Okay, welcome everyone. In today's lecture, we are going to be using Castigliano's method to analyze a simply supported beam. Okay. So what are the objectives here? The main objective is to apply Castigliano's theorem to a simply supported beam to calculate the slope and deflection at a particular point in that beam. In the previous lectures, we have mostly looked at cantilever beams, so it is going to be a little bit different. Okay, so let's look at first the example of finding the slope of a simply supported beam. Okay, so in this case, you essentially have a simply supported beam here that is supported at point A and point C, and you have a 400-pound force acting at this point B. The point B is 40 inches from A and 20 inches from C. And we are asked to find the rotation at point B, given that the bending rigidity of this beam is 20 times 10 to the 6 pound inch square. Okay. So this problem is a little bit different from pretty much all the problems we have looked so far. So if you look at problems that involve cantilevers, in most of the times, we can essentially avoid finding the reactions. Okay, because you can always start from the free end of the cantilever, and if you do that, you don't have to find the support reactions. But in the case of a simply supported beam, that is not possible. You essentially have to find the reactions at point A and point C. Now, in this particular problem, we have a force of 400 pounds acting at point B, but we are not asked to find out what the deflection at point B is. We are asked to find out what the rotation is, which means that you essentially have to assume a dummy moment at point B. So that dummy moment in this case, I assume that to be m0. And in this particular case, I am assuming that this m0 is in the counterclockwise direction as it is shown here. Okay, so the moment m0 is in the counterclockwise direction. Now, we have to find the reactions RA and RC. Okay. Now, to find these reactions, we essentially have to also consider this moment m0. Okay. Even though this moment is a dummy moment or a fictitious moment, for essentially calculating RA and RC, we have to take into account m0 along with the 400-pound force. And the reason is, in that way, you will get RA and RC in terms of m0. So if you write the moment function along the length of the beam, then those moment functions will be in terms of m0. So then you can take the derivative with respect to m0, and that essentially will give you the rotation at point B. Okay, so that is why we have to consider m0 also in terms of finding RA and RC. Okay, so simply you essentially have this force equilibrium. RA plus RC should be equal to the external force, which is 400 pounds, and then you take moment about point A. Then you can find out by moment equilibrium that RC, which is the reaction at point C, is 16,000 minus m0 by 60, and the reaction at point A is 8,000 plus m0 by 60. Okay, so essentially RA and RC are found. Now, once we know RA and RC, we can find out what is the moment function between A and B and B and C. Again, there is going to be a discontinuity in the moment function, so you'll have separate moment functions for the segment AB and the segment BC. Okay, and again, we have seen these things multiple times previously. Okay, now so let's look at the segment AB. It is fairly easy to find out what the moment m inside the internal moment in segment AB is. I denote it by m1 here because m1 is going to be different from m2, which is the moment in the segment BC. Okay, so you can easily find out that m1 of x is nothing but 8,000 plus m0 by 60 times x. Okay, so that is your internal moment in segment AB. Now you can also do the same thing for segment BC. So typically, in most of the previous cases, what you would do is something like this, right? You will essentially take a section between B and C, and then you will have this moment m0 that is acting there. Then you would have this force P equal to 400 pounds that is acting there. And then, of course, you have the reaction RA acting there. Okay, and then we will have this, it could be a V2 of x, it could be like that, and there could be an m2 of x. Okay, so typically, if you still go from left to right and take a section between the point B and point C, this is how your free body diagram would look like. Okay, you can of course do the problem like this. You can find out what m2 of x for this particular configuration is, and of course you can integrate and so on. Okay, but for problems like this, when you have a simply supported beam, sometimes it's actually a lot more advantageous to actually start from the other side. So if you go back a slide, instead of actually taking a section here and considering this left-hand segment, it actually is better to consider the right-hand segment. So if you do that, then you're going to be much simpler. You're going to end up with a much simpler free body diagram because there is only going to be RC here. Okay? You don't have to worry about the 400-pound force. You don't have to worry about m naught. So it becomes much, much simpler to write the moment function. Okay? And that is what I have done here. So essentially, I have taken a section between B and C, but now considered the right segment. So this is my point C. Okay? And this is the section I have taken between A and B, or between B and C. Okay. Now, if you look at what the moment function is, this m2, it's actually very, very simple. Okay, it is just 16,000 minus m naught by 60 times x1. The key difference though is that I am now defining my x1 going from right to left. Okay, so at point C, x1 is 0, and at point B, x1 is going to be 20 inches. So when I integrate this function, m2 of x square, to find the strain energy, I have to integrate from 0 to 20, not 40 to 60. Okay, so this is something that is very important. So if you change the segment that you're looking at and you're looking at a different coordinate system, then you have to put the appropriate limits for that coordinate system. So I am defining x1 here from right to left. So essentially my limits for x1 will grow from 0 to 20. Okay, so that is something that you must keep in mind. Okay, once you keep that in mind, it's actually very simple. So theta b, which is going to be the rotation at point B, is still going to be del u by del m naught, which is going to be the integral from 0 to L, m over ei, del m over by del m naught times dx. Of course, this m is the internal moment function. And of course, this m naught is the dummy moment. Okay? So again, I want to emphasize that you take the derivative with respect to the moment, the dummy moment, not with respect to x. Okay? But now when I do the integral from 0 to L, my first integral, this is for segment AB, and the limits run from 0 to 40. So 0 to 40 of m1 of x by ei, del m1 by del m naught dx. The second integral is for segment BC, but now I do the integration with respect to dx1, not x1. Okay, so I'm doing the integral with respect to x1, not x, which means my limit is going to be from 0 to 20. Okay? So if you can keep those in your mind, then actually it becomes very simple. So now I can take del m1 by del m naught, which is x over 60, and del m2 by del m naught is going to be minus x1 over 60. Okay? Then I plug in those values into these two integrals, which is what I have done here. Okay? And then you do the integration. And if you do the integration, at the last step, you can put m naught equal to 0. Okay? Because you've already taken the derivative of u with respect to m naught. And since m naught is a fictitious moment, you can say that m naught is equal to 0 in this final equation and then do the integration. So now if you look at the final equation for theta b, it's actually very simple. It's essentially just integrating two terms. Okay? And if you do the integration and substitute the limits, you're going to find that the rotation at point B is 1.777 times 10 to the minus 3 radians. Okay? It's not in degrees, it's in radians. Okay? It's a fairly small number, but that is what you would expect in most cases. Okay? And the theta b also turns out to be positive, which means that the direction of my assumed dummy moment is the correct direction of rotation. So if you recall, we assumed that our m naught is in the counterclockwise direction. The fact that theta b is also positive means that the rotation at that particular point B is positive. So if you think of the simply supported beam to start with, now as you deform, it is going to have, that's probably a little too exaggerated. It is going to be something like that. Okay? So at this point B, the slope is small, but it is positive. Okay? And that is what this particular value indicates. Okay? So this problem is a little bit different from a lot of the problems that you've seen so far. So the first thing we notice is that we have to write the reaction in terms of both the applied force and the dummy moment. Then we chose to use different coordinates for writing the moment functions for segment AB and segment BC. And if you do that, you have to make sure that you substitute the right limits for integration. But that actually makes your calculations a lot more simpler. Okay? So if you have a lot of time on your hand, you can try writing the moment function the regular way and try to integrate it. okay, and see how much messy it is, okay? And you will thank me for telling you that this is an easier way, okay? Anyway, so that is the way to kind of look at simply supported beams and to find rotations, okay? Now let's look at the same example, but instead of finding the rotation at a point, we'll try to find out the deflection at a point, okay? So essentially, it's the exact same problem. So the same forces are being applied, it's the same length, the same EI and everything, except that we are now asked to find out what the deflection at point B is, okay? Now, in this case, you have an actual force acting at point B, but still we have to consider it to be a variable force because we eventually want to take the derivative of the strain energy with respect to that variable force. So even though there's a 400-pound force acting, we'll assume that the force acting at point B is just P, okay? There is a mistake here. This should be RC, which is probably very obvious to you. So it is the two reactions RA and RC, and we can find out the reaction RA is P over 3 and RC is 2P over 3. Okay, and I think this is very trivial for you to do it. So essentially, the main point here though is that we again find the reaction in terms of the variable force P. And the reason we do that is that when we write the moment function will also be a function of P. If you just use P is equal to 400 pounds and then find RA and RC, you will essentially get numerical values, and then your strain energy will not be a function of P. It will be just a particular constant value, okay? And then you can take derivative with respect to anything, okay? So that is the reason why RA and RC should be in terms of P, okay? Now, once you do that, we actually use the exact same method. We take a section between A and B, and the x goes from left to right. You find out what m1 of x is. That is nothing but px over 3. For the segment BC, we go from right to left, and we define x1 to be going from right to left. So then m2 of x also comes to be very similar or very trivial. It's 2p over 3 times x1. Then del m1 by del p is x over 3, and del m2 by del p is going to be 2x over 3. Okay, so it's actually very, very simple. And then once you have that, you can essentially use the equation for finding the displacement, which is nothing but integral 0 to L of m by EI times del m over del p times dx. That is exactly what you're going to do. So this is the segment AB, the integral for that, and the segment BC. And again, you notice the integration points, it's from 0 to 20, not 40 to 60, because we're integrating with respect to x1. Okay? And if you do the integral, again, it turns out to be fairly easy, and you get the displacement at point B to be equal to 0.0711 inch. Okay? It's a small value, but that is what is typical in most engineering structures. You don't get large deflections. Okay? So this is how you find the deflection in a simply supported beam. The main difference between this and the cantilever beams that you have seen so far is that we had to calculate the reactions. And we had to calculate the reaction in terms of these dummy moments and as well as the dummy loads, or in some cases the actual loads, but variable loads that are being applied on the beam. Okay? So in the next lecture, we will look at a more complicated, a more complex structure which can also be analyzed using Castigliano's theorem, especially when there are multiple forces involved. Okay? So we'll look at that in the next class. Thank you.